So yeah, fine. So today we will talk about week 3, assignment 3, previous year question paper on the topic of nuclear and particle physics. So let's talk for the first question. The first question is explain the statement, is it right or wrong? The first excited state of calcium 2041 is found to have IP equals to 3 by 2 minus, which is explained within the single particle cell model. So as this question is very much common to the previous week assignment questions, so we will do quickly for this question at least. So I think this question is very much simple. Like they are asking that whether the first excited state of calcium 2041 have a IP equals to 3 by 2 minus, or if it is correct, that can be well explained within the single particle cell model. So obviously we know that what is single particle cell model. So if this calcium 2041 ground first excited state will have IP equals to 3 by 2 minus, which can be explained by the single particle cell model, then the statement whatever it is given here, that will be correct one. Okay, that will be right one. So we'll check that it will give IP equals to 3 by 2 minus or not. Okay. So for the first excited state, so as we were talking for the last class elaborately what will be the spin and parity for the ground state and the first excited state, as well as for the second excited state of any nuclear system. So today we will not do all the elaborate calculations, all the elaborate explanations, but still we will do a little bit to answer the first question at least. So for calcium 2041, Z equals to 20, as I already know, and then A equals to 41, so obviously I can write it as N equals to A minus Z, right? So that will be 41 minus 20, which is 21. So this is already fine. So and also one may see that okay, the for the nucleon as Z is 20, so that means it is an even number. So it will not contribute to the spin and parity for this nucleus, but for N it will be 21, so that will contribute to the spin parity for this ground state calcium 2041. But obviously it is talking about the first excited state, but we will check that what will happen in the first excited state. So for 21, right? So N equals to 21. So if N equals to 21, I have just plotted the same figure whatever it was there previously also. So here up to this it was 20, field 2, 8, 20, up to this it is 20. So as N equals to 21 in the ground state, so what will be the last one? Last one will be here. Simple. And where it will be? And here how many nucleons will be? Here 4 particles will be there, because it is 1d 3 by 2. So d 3 by 2 means obviously there will be maximum number of nucleons will be 4. So 1, 2, 3, 4. So this is for neutron, right? So for proton, how much it is? For proton, let's say Z, I'm writing here with a different color. It's already known to all of you, but still for the completeness I'm just saying these things. So Z, for Z case it will be like this one. Okay. So now I'm changing the color again, plus this one. So that was the configuration for the ground state. Now they are asking for the first excited state. So for first excited state, what will happen? Obviously, as this is the single one, that will go here. That we will not. We all know that. So the latest one will be the for first excited state. For first excited state, the configuration for the the outermost orbital configuration will be like 2p 3 by 2 and 1, because only one particle will go from here to here. Okay, so that means 2p 3 by 2 will be the outermost orbital configuration, nuclear orbital configuration. So for that case, what will be the IP value? They are asking for the IP value. So I is nothing but 3 by 2 as it is given here, total spin. For P is nothing but minus 1 to the power L, right? So what will be the L here? L will be like, for as I already told so many times before, that if L equals to 0, that means it gives the S state. L equals to 1, which will give the P state. L equals to 2, which will give the D state. L equals to 3, which will give the F state, like that. So as you can see that 2p 3 by 2 1, so obviously p is there, that means it will have n equals to 1 for this case. So if I write here minus 1 to the power 1, that will be minus 1, which is negative value. Negative value. So for IP case, for calcium 20 41, for that case in first excited state, the IP value will be, IP is 3 by 2 minus. Okay, so that will be the 3 by 2 minus case. So obviously whatever the statement was there, the statement was that IP equals to 3 by 2, which can be explained well within the single particle cell model, and we just explained the single particle cell model, and it was totally explained very well with the single particle cell model itself. So that whatever the statement is there, that is exactly correct. Okay, so the statement is right. Okay, fine. Now we can come to the next question. Oh, I gave up so much space. Okay, now for this question as well as for the rest of the questions, whatever it was there, it is there for the week 3 assignment. That will be totally based on the radioactivity. So I hope all of you have already known about radioactivity, because Professor Paulus has already gave some lectures on the radioactivity element and reactive element and radioactivity. So we all know what is radioactivity, but where the question will come, I will tell wherever it will be needed. Okay, a little bit more. So for the question number 2, what is the question? First we will see. The activity of a sample of radioactive element is found to be 180 per second. If its half-life is 31.58 seconds, the number of parent elements present in the sample now is how much? Okay, so this is the question for radioactive element radioactivity chapter, and for the radioactivity chapter, what we need to know only one expression, that is n equals to n0 e to the power minus lambda t. That is the for radioactive total chapter, we need to know only this expression, because this expression is the, you can say that this expression is the parent expression for all the subsequent expressions. So whatever the other expressions or whatever we need to calculate for the radioactivity chapter, this one is the main expression. Okay, n equals to n0 e to the power minus lambda t. What does this means of these elements? So n0, let me write here. So let's say one radioactive element is there as X, it is going to decay to Y. Okay, fine. So the first parent nucleus was X and the daughter nucleus is Y. Now what is N0? N0 means the number of parent nucleus at time t equals to 0. That is N0. Now coming to N. N is what? N will be at time t, how many number of atoms will be present in the system for the parent case. How many parent atoms will be there in the system at time t equals to t. Okay, so N0 and N we already got to know. What is lambda and t? T is obviously the time, and lambda is the half-life. Half-life means the time at which half of the parent nuclei will decay to the daughter one. Okay, so n equals to n0 e to the power minus lambda t, that will be nothing but a decay, decreasing function, because e to the power minus lambda t is there. So we can see that obviously whenever the radioactive element will be there in the system, that will going to be decay to another system, and we are going to calculate how many remaining parent atoms are present at time t equals to t. So obviously what will be the what will be the number of daughter particle? That will be simply n0 minus n, because previously it was n0 for x, and right now n is for x, so whatever the value will be for y, it will be simply n0 minus n. So this is the one and only expression for radioactive chapter. Okay. Now in that question what they are asking? They are asking that activity of a sample of radioactive element is found to be 180 per second. So what does this means of activity? So I have written the definition of the activity. Activity means the total decay rate of a sample of one or more radioactive nuclides is known as the activity of that sample. So what does this means? The mathematical expression for the activity will be minus, let's say I am writing here activity as A minus dN dt. So this is activity expression, mathematical expression. So now as I told you that the parent expression for radioactivity chapter is n equals to n0 e to the power minus lambda t. So as this is the parent expression, so if I want to calculate dN dt, then what will happen? dN dt will be simply n0 is a constant, then minus e to the power minus lambda t, and then 1 lambda will come. So I have just written that one, and as it is as a negative sign, so obviously the activity will be minus dN dt. So it will come as n0 lambda e to the power minus lambda t. Now you can see that n0 e to the power minus lambda t, that is nothing but n. So activity we can write in terms of lambda into n. Okay. So in that question it is given that the activity is given as a 180 per second. So whatever the unit is already given, that I am just including here 180 second inverse. Hello? Maybe I was totally out of the connection. The same thing happening again and again. Okay, sorry for these things, and I'm going to share my screen again. And I was totally explaining all these things. So can anyone confirm me, like up to which did you hear or something, like question number 1, question number 2, did you hear all these things?
Yes, ma'am, it was audible. Only for some time you went out of the meeting.
Okay, sorry. Okay, so activity, did you hear that one? What is activity and what was the expression for the activity and minus dNdt and how it has come?
Yes, ma'am.
Okay, fine, very good. So in that question it was given that, yes, in that question it was given that the activity is 180 per second, okay, and also it was given the half-life of X is 31.58 second. So A is already given and T is already given. I mean T half. T half is half-life. So lambda is how much? Lambda is 0.693 divided by T half. It is nothing but ln2 divided by T half. Okay. So that means you can see our A is given, our T half is given. From T half we can have the value of lambda by taking 0.693 divided by T half expression. So now they are asking what will be the, okay, what they are asking? They are asking here what is the number of parent elements present in the sample now. That means they are nothing but asking about capital N, because capital N is nothing but the number of parent elements at time t equals to t in the system, right? So as we can see right now, A is given, lambda is given, so obviously N can be written from A equals to lambda N, and which is nothing but A by lambda. So A is already given 180 and lambda is 0.693 divided by T half, and if I calculate these things it will come as 8202.59. But you can see this should be a number. That means how many number of parent nuclei will be present at time t equals to t. So that should not be any decimal place digit. So obviously in nearest integer value we have to write our answer. So the answer will be 8203. Okay. think I am here. Okay, fine. So, okay, now coming to question number 3. Is it understandable whatever it was there up to question number 1 and question number 2 for all of you? If you have any doubt, you can just ask me anytime during the session. There is no problem on that. Just unmute yourself and tell me. Okay? I think there is no question. Okay, in chat box also there is no question. Then it is fine. I'm audible, right?
Yes, ma'am.
Okay, fine. Okay, so question number 3. The activity of a sample of radioactive element is found to be 432 per minute. If its half-life is 1.5 minutes, the number of elements in the sample is how much? It's exactly similar whatever it was there as question number 2. So I'm quickly write the expression. The expression was activity is equals to lambda n, as we have calculated that one as minus dn dt. And what is t half? T half is given as 1.5 minutes. Okay, I'll tell one more thing here. Okay, and a is given as 432 per minute. Now, if t half is given, so what will be lambda? Lambda will be 0.693 divided by 1.3. And what is the unit of this? This will be minute inverse, because this is in minute, and so whatever the whatever the dimension of lambda will be, that will be minute inverse. Okay. So now A is lambda into n. So they are asking the number of elements in the sample. So the number of elements means they are asking about number of parent nucleic atoms. So n is A by lambda. So A is 432. Now just see, it is minute inverse. Like I can write it like 432 minute inverse. Okay. So we don't need to convert that minute inverse into the second inverse. If it is also second minute inverse, then we don't need to convert this to unit, because this is nothing but a ratio. So ratio means obviously the minute inverse will cancel out. But let's say if our activity is given in second inverse, let's say, and our half-life is given in minute. So obviously we have to convert in one case. Like let's say minute can be converted in into second, or second can be converted into minute. Whatever you prefer, that will be for your convenience. Okay. So I am telling that you should be consistent with the unit throughout the calculation. But here in that calculation you can see this is also per minute and this is also minute. So the lambda will be obviously for per minute, and A is also per minute. So N will be simply 432 divided by 0.693 into 1.5. So if I calculate this value, then I am going to calculate that one, 432 into 1.5 divided by 0.693. So this is coming as 935.06. But as I already told you that n is nothing but a number, so whatever it will come, it will be a integer. So n will be 935. So that much atoms are present right now at t equals to t in the sample. Now for completeness, just see what will be the value of n0. How we can calculate n0? N is n0 to the power minus lambda t. Okay. I think number of, okay. Now the time is not given here, so we will calculate that one in next question. Okay, no problem. But till now, you can just calculate up to n what will be the value of n here. So that is exactly similar whatever it was there for the previous question. Okay, so maybe we can go to the fourth question. Fourth question is calcium 2040 undergoes beta decay to scandium 2140 with half-life of 9.435 minutes. Starting with a fresh sample of 1000 atoms, how many present atoms will be there after 28.305 minutes? So I have already told you that this is also a radioactive question. So obviously the parent expression will be n equals to n0 minus n equals to n0 to the power minus lambda t. Okay. So for this case, calcium 2040 was there as a parent one. Now it will decay by beta decay with the half-life I can write it like half-life with scandium 2140. So this is the radioactive process. So this is the parent and this is the daughter. So now it is given already that what will be the half-life of calcium. So that means T half is already given, that is 9.435 minute. Okay. Now starting with a fresh sample of 1000 atoms, that means N0 was given as 1000. How many parent atoms? Parent atoms, I already told you that parent atoms for this case is calcium 20. So what they are asking? They are asking for how many parent atoms will be there after 28.305 minutes. That means they are asking nothing but N, and T is already given as 28.305 minute. Now see the dimension also, like this unit is in a minute, this unit is also in a minute. So obviously there should not be, we don't need to change any minute to second or second to minute like that, because it is already given in minute, this is also given in minute. So it's fine, very good, that N equals to 1000 is given e to the power minus lambda into 28.305. So what will be lambda here? Lambda is nothing but ln2 by t half. So ln2 is 0.693 divided by t half is how much? 9.435. 9.435. So our N is 1000 into e to the power minus 0.693 divided by 9.435 into 28.305. Okay. Now we need to just calculate that one. 0.693 divided by 9.435 into 28.305. So that is, okay, I am going to write each and every steps. So 1000 into e to the power minus 2.079. So e to the power minus answer is this much. 1000, am I audible? I hope so. 1000 into the power into 0.12505 something. So if I just multiply with 1000, then it is coming as like 125.05. Now you can see obviously N should be in integer number, so it will be 125. Now you can see just the numbers right now. Previously N0 was 1000. Now calcium is going to scandium. So it was previously 1000 at t equals to 0. But at t equals to 28 point, how much? 28.305. At this point, our calcium becoming as 125, because rest of the 1000 minus 125 has been converted to scandium 21. So how much has converted? 1000 minus 125. So it will be 875. That much atoms, calcium atom has already changed to scandium 2140. They are not asking about this one, that will be the daughter atom's nucleus, but they are asking about up to 125. Okay. Okay. So coming to the next question. Calcium 2045 undergoes beta decay with half-life of 163 days, starting with a fresh sample of 2000 atoms, and know in the sample how many atoms will be there after 326 days. So the same thing was there right now. Previously it was parent, and it will decay to someone else. Let's say y I am writing here. We don't know what about y. We don't need to know also that one. And it is going through beta decay. Half-life is already given as 163 days. Now see the unit here. They are writing it as a days. Okay, but here also it is given in days. So obviously there is no need to convert these units. So starting with a fresh sample of 2000 atoms, that means N0 is 2000. How many atoms will be there after? T equals to 326 days. Okay. So simply same expression, n equals to n0 e to the power minus lambda t. N0 is 2000 into e to the power minus lambda into 326. And lambda can also be calculated. So n will be 2000 into e to the power minus 0.693 divided by t half. T half is given as 163. 163 into 326. 326. So if I just calculate that one, 0.693 divided by 326. I'm sorry. 169 into 326. So it is 2000 into e to the power minus 1.336. So e to the power minus answer, that is 2000 into 0.2626. So it is coming as 523.37. So it is 525. So that much parent particles, and how many atoms will be there, that will be remaining as a parent particle after 326 days. Okay, so I hope you understand the question and the answer as well. Because you can see that the question number 5 and question number 4 are exactly similar. So we just need to put n equals to n0 e to the minus lambda t, and n0 is given, lambda is given, t is given. So obviously we can get the value of n. Oh, I have already written here. I mean, it is not exactly 500. You can just, if you just calculate that one, it is like 525 something, whatever I have written here. Yes, 525. It's nearly 500, but yeah, fine. It is 525. Okay. So now question number 6. This question is little bit tricky, so we need to see that one with care, and after that we will answer the question. Till now there is any problem after question number 5? I'm audible, right?
No, ma'am, no problem.
Okay, fine. So question number 6. Just see the question, because this is little bit tricky. I'm going to read that one very carefully so that you can understand each and every sentence. A pure sample of TY 66150 contains 1 lakh atoms at time t equals to 0. So from this sentence, obviously we can directly tell N0 is 1 lakh. Is it correct? Is it understandable by everyone? Because at t equals to 0, they are asking that a pure sample. That means Ty was the first one as a parent nucleus, and that will be going to decay to another nucleus that we will see later. But at the time of the first sentence, it is showing that N0 is 1 lakh for dy 66150. So I am going to write here dy 66150. That is the parent nucleus. Okay, and N0 is given. It radioactive decays 64% to Tb 65150 and 36% to Gd 64146 through beta plus and alpha decays respectively. So what does this mean? This is a little bit big sentence. This means that our dy66, that was the parent nucleus, it is going to decay in two ways. In first way, it will decay through beta plus and it will become as TB65. In the second way, it will decay through alpha and it will become as ZD64. Now, what is the percentage of doing these things? So, the first process will be in 64% and the second process will be in 36%. What does this mean? This means that, let's say I have 100 dy sample. Among this 164 dy will convert to TB and 36 dy will convert to ZD. Okay, it's very simple. I mean, this is the pictorial expression for this sentence. After 1 minute, after 1 minute means t equals to 1 minute. The sample contains 5900 atoms of TB. Just focus on this line. They are right now telling that the number of TB is 5900. Okay. Now they are asking what will be the half-life of dy in minutes. So if first of all we just need to check the dimension and unit for this question. T is given in minute and the half-life is already also asking in the unit of minute. So we don't need to change any unit here. Okay, fine. So N0 for dy at t equals to 0 was given. TB at t equals to 1 minute is given, the number of TB, and they are asking for the half-life of dy. Okay, very good. Okay, right now I will not show this one because we need to understand by ourselves. So dy 66, TB 65, it was 64%. And there was another one which is GD 64. Okay, and this is 36. As there is N0 given and also NTB given, and there is no information about the GD, so for this question we will little bit focus on TB only, not the GD. Okay, now we will focus only on this one. dy is going to TB. This is 66, this is 65, and this is 64%. So now you can see our N. Okay, they are asking that after 1 minute. So whatever our parent expression is there, N equals to N0 e to the power minus lambda t. That is exactly everywhere applicable. So N means what? N means the number of dy atoms after t equals to 1 minute. Is it fine? I hope so. Yes. So N0 was 1 lakh. Lambda we don't know. Obviously, if I know lambda, then only we can have the value of t half, because lambda and t half is related with lambda equals to 0.693 divided by t. We know t. T is 1 minute. So how much we know? We know N0, we know t on this parent expression. But also we know one thing. We know what? We know that our N minus N0 should be what? N minus N0 should be TB or GD. But 64% should be TB. Right? Because 64% was TB. So whatever is there, that means 1 lakh. Now I will go here because yes, 1 lakh is there. N1 dy means dy is going to TB and GD but as for TB it was 64%. We will focus only this part. So n will be how much? N will be, as I told you, n0 minus something. So something is how much? 5900 is for TB, which is 64%. So 64% of 1 lakh, that will be 1 lakh minus 5900 into 100 by 64. That will give us N1 dy. Okay. So now if in any question they were, let's say in any question they are giving the value of GD at t equals to 1 minute. So what we will do for that case, let's say x is the number of GD at t equals to 1 minute. So for that case what we will say? We will say N1 dy is 1 lakh minus x into 100 divided by 36. Okay. So this is the main trick for this question. We need to know capital N, because if I need to know if I know the value of capital N, and also we will obviously know the value of N0, we also know the value of T, then we will know the value of lambda. From that lambda we can know the value of T hat. But how do I know the value of N for dy? That is the expression, it is written here. N for dy is nothing but N0 minus N at t equals to 0 for TB into 100 by that much percentage, because it is going to decay in 64%. If they will ask about GD, then that should be 100 divided by 36. So if I got to know the expression and the concept, then we will simply calculate capital N, and obviously you know that from capital N, N0 e to the power minus lambda t is there. Lambda should be ln 1 lakh divided by 90781, and that will give us 0.09672. So the half life will be simply 0.693 divided by lambda. That will give me as 7.17 minute, because all the things are given in minute and minute inverse and all these things. I am audible. Okay, fine. So for this question only we have to check that which decay mode they are going to focus and how much percentage is present in that decay mode. In that decay mode, dy to TB 64% is given and TB number of sample is given. So obviously we will focus on this decay channel only, and for that case N0 minus at time t equals to 1 minute whatever the number of TB was there divided by 64%. That's it. So that is the calculation for getting N of dy at t equals to 1 minute. If I get the value of N, then N0 is given, T is given, we can have the value of lambda. And from the value of lambda, we can have the value of T. So as there is only one line a little bit tricky, so that's why I told you to have a very simple slow by slow process so that we can understand this question and the answer as well. Okay. So now question number 7. Radon-222 is a radioactive element with a half-life of 5 days. Radon-222, it has the half-life of 5 days. It decays on that much. Which element after 1 alpha decay? So this is a very simple question, because here they are just only asking our parent nucleus is radium 222. What will be the daughter nucleus after 1 alpha decay? And whatever it is given as a half-life, that is no need for this question at least, right? For this case, I just need to know one thing. What is the Z value of radium? Obviously, we can't remember all the elements Z value and A value in the periodic table, but maybe we can have a little bit idea for most popular radioactive element. So for this case, I have written here the radium is 86. The Z value for radium is 86. Now you can see, if radium is 86 222, then maybe I can write here radium 86 222. So it is undergoing alpha decay. So what will be the particle here? So alpha is how much? Alpha means it is nothing but He24 plus, 2 plus, right? So like helium, ionized helium nucleus only. Helium nucleus only is known as alpha. So if it is alpha, that means 2 will be deducted from here. Let's say this is X. 2 will be deducted means it will come as 84, and 4 will also be deducted from here. It will be 218. So that is the new particle after 1 alpha decay. So now you can see the periodic table, and in the periodic table you can see that 84 is nothing but it consists of polonium, which is polonium 84 218. Now you might ask me one question that for this question, so should I need to remember that Z and at least Z value for all the periodic table particles and elements. So for that question I will tell, obviously you should not remember all the particles Z value, because it's like 120 or more than 127 right now particles are there. No, 121 particles are there, more than like that. So obviously we can't remember all the elements Z value, but we can remember at least some of them which are very popular. So like let's say uranium 92, then radium 86, then polonium, then iron, and then xenon. These type of things, like this type of elements which are very much radioactive as well as very much famous as also. Like for iron, why I am telling as iron, this is not a radioactive element, but this is a very stable particle, and this is a very famous and this is very popular one in nuclear particle physics chapter. So iron, you just remember the Z and A value. Xenon, radon I have already written, polonium, uranium, this type of things. Not that much whole things, but little bit more you need to remember. But I have seen most of the questions, they have already given the Z and A value for radon, let's say 222, and they are asking that what will be the Z and A value for the element daughter particle after 1 alpha decay. That they can ask. So for that case, we don't need to remember what is the element for, let's say Z equals to 84. Okay, so question number 8. Up to question number 7, is there any question till now? I think I am audible. Yes, I am audible. If you have any question till now after question number 8, then 7 you can ask me, or otherwise we will move to the question number 8. It's fine, right? Am I audible? Yeah, okay. Very good. Okay, so coming to the next question. AFAD 87-200, alpha decays to 80-85 196. Obviously, these particles, AFAD is very much not that much common to all our nuclear particle physics course. So we don't need to remember Z and A value for AFAD. because it's already given in the question. So A for 87,200, that is going to decay by alpha with aceton 85,196. Oh yeah, okay, fine. You can see why it is alpha, I mean after alpha decay, why it is coming as 85,196, because as I already told you, this is nothing but 2 4, 2 plus, that means the nucleus of the helium. So 2 is there, so 87 minus 2 which will be 85, and 200 minus 4 which will be 196. So A for 87,200, alpha decays to 80, 85,196 with a very short lifetime. Mass of A for 87,200, 80, 85,196, and the alpha particle are this respectively. Compute the Q value of the reaction in MEV. Okay, so the expression is like A for is going to 80 plus alpha. So they are asking about Q value. So for Q value calculation, it is nothing but the mass of parent particle minus the mass of daughter one. So what are the daughter particles? 80 and alpha. So this is the Q value. Now you can see here, whatever the value of mass for A for 80 and alpha are given, it is given in U unit, that means atomic mass unit. We need to convert that one in MeV, because the Q value they are asking in MeV unit. So 1 U is 931.5 MeV. That was already discussed in the, I think, week 1 or week 0, that the conversion rate of one atomic mass unit, and the MeV is 1 U equals to 931.5 MeV. So if it is like that, then what we need to do, we need to simply put here the mass of this into 931.5, that will be in MeV unit. So maybe I can do, this is 200.00657 minus 195.99579 minus 4.00260. So that will be the Q value. So let me calculate here, 200.00657 minus 195.99579 minus 4.00260. Okay, that is 8.18 into 10 to the power minus 3 into 931.5 MeV. So that will be 7.61 MeV. Actually it is 9, so it is 7.62. So give up to 1 decimal place, that means 7.6 only.
Ma'am, we don't need to multiply this term of the masses total with C square, right? We have to, right?
Yeah, because it is in MeV range, MeV. So MeV is already taking care of C square and all these things. So we don't need to calculate the C square again. Okay.
Okay, ma'am.
Only we just need to do the mass difference between the parent nucleus and the daughter nucleus. That's it. Okay, and one more thing is there, as in that question it is not given. Okay, I can tell you one extra thing. There it is given as mass, but they are not giving the exact definition of mass. Like, what does this means of that mass of A5? Is it the atomic mass or it is the nuclear mass? If the nucleus mass of A5 is given, nuclear mass of AT is given, nuclear mass of alpha is given. Obviously alpha is nothing but a nucleus only. There is no electron outside of that alpha particle. So for alpha particle it is fine. There is no problem. But the mass of A4, if it is given as mass of A4, there is not that much clear information that it is the atomic mass or it is the nuclear mass. If it is the nuclear mass, then whatever I have written here, that will be exactly correct. That means the nuclear mass of A4 minus the nuclear mass of AT minus the nuclear mass of alpha. That should be the Q value. But let's say if it is an atomic mass, I think I will teach that one in the next week also, like what will be the difference between atomic mass and a nuclear mass, and how much we will, how we can deal with the Q value calculation in the atomic mass and nuclear mass. So here also I am just telling a little bit for completeness. If it is a nuclear mass, then it is fine, no problem. Nuclear mass, and this is also already a nucleus, so no problem on that. If it is a nuclear mass, then Q value, whatever I have written, that is exactly correct. But let's say it is an atomic mass. Atomic mass means, okay, maybe I can write here. Let's say atomic mass of FR I am talking. So FR is how much? FR has 87,200. 87,200. So atomic mass of FR is 87,200. Let's say atomic mass of FR 87,200 is given. But in Q calculation, we need nuclear mass of FR 87,200. So if atomic mass is given in any question, but we need to calculate the Q value, and the Q value is obviously on the basis of nuclear mass, then what we have to do? We should convert that atomic mass to the nuclear mass. Otherwise the calculation will be a little bit wrong. Okay. So how to do that? Let's say I am writing here mass of atomic. Okay. Mass of atomic, like Ma is atomic mass of Fr. That is equals to, atomic mass means what? Atomic mass means it is nothing but the nuclear mass plus electron mass. So M N Fr, that means nuclear mass of Fr, plus how many electrons are present here? 87, right? 87 electron, and each electron has mass Me. So this is the expression for atomic mass, and there is a conversion relation for atomic mass and nuclear mass. So for this case, MnFr can be written as MaFr minus 87 into Me. And we all know the value of Me. The value of Me will be like 0.511 MeV. In unit of MeV I am talking. So 0.1511 MeV. Then we can just put the value of 0.511 into 87. Then the value will be whatever. That should be subtracted from the atomic mass of Fr. Then we can got to know what will be the nuclear mass of Fr. So why I am telling that one? Because in this week it is not that much problematic. But when we will go further, there we will face something as a atomic mass, nuclear mass, what will be the value of Q value, and all these things. So for that case, we need to take care about the electron mass as well. Okay. Okay, I just did a little bit extra thing, but yeah. So now coming to the question number 9. Radium 86210 alpha decays to polonium 84206 with a very short half-life. Mass of radium, polonium and the alpha particle are given as this and this. Compute the Q value of the reaction in MeV. This is exactly similar whatever we had done just right now. So mass is already given, parent nucleus mass is given, daughter nucleus mass is given, as well as alpha particle mass is given. So here I am assuming that the mass means it's only the nuclear mass. So for this case, simply we will do 210.45657 minus 205.8878 minus 4.00260 whole into 931.5, and it will be in MeV unit. So just let me calculate that one. 210.45657 minus 205.8878 minus 4.0026. Okay, that is 0.56617 into 931.5. That will be 5 27.38 MeV. So give up to 1 decimal place, so obviously it will be 527.4 MeV. So maybe I have written here. Hmm? 31.5. Did I do any mistake? Okay, 527 will be there. Okay, fine. And 31.5 into 0.56617. Okay. So that will be 527.38. So 527.4. Okay. Okay. So coming to the question number 10. Up to this, is there any doubt? I hope no. I am audible? Yes, I am audible. Okay, so question number 10. An element with atomic mass 120, alpha decays with Q value 8.2 MeV. The kinetic energy of the particle is how much in MeV? Give up to 2 decimal place. An element, let's say X, is going by alpha decay 2y. The Q value for this reaction is 8.2 MeV. And atomic mass for this element is 120. So obviously I can say here what will be the value, atomic mass for Y, that will be 116, because this is 2, 4. We don't need to know about this value and this value in this question. So that's why they are not given these values. Alpha decays with Q value 8.2 MeV. The kinetic energy of the alpha particle is how much? That means they are asking what will be the kinetic energy for alpha particle. So just see that expression. This is the expression. The Q value in terms of the alpha particle kinetic energy. This is Q, this is E, means the kinetic energy of alpha particle, plus E into M by MD. What is M and what is MD? Okay, I am writing here. E, MD into E plus M into E divided by MD. That can also be written as Q equals to MD into Q equals to MD into E plus M into E. So there is a derivation of this kinetic energy and the mass number and the Q value expression. I think sir has already explained that derivation, but if sir did not do that, then maybe I can do in the next class or this class also, if the time will permit. But for now you can see, as it is already given here, the Q value is kinetic energy into 1 plus M. M is the mass of the alpha particle divided by MD. MD is the mass of the daughter particle. So the mass is nothing but, right now we will talk about the atomic mass. Okay? Obviously the mass of the particle and the atomic mass of the particle is not exactly similar, but for the sake of simplicity, as there is no other information about the exact value of alpha particle and exact value of daughter particle, mass of daughter particle, we will take the mass of the alpha particle as the atomic number of the alpha particle, the mass of the daughter particle as the atomic number of the daughter particle. Okay? So, if Q equals to given as E into 1 plus M by MD, then E can be written as Q divided by 1 plus M by MD. Now what is M and MD? Okay. So what is M and MD? For X 120 goes to Y 116 plus alpha 2 4, AM is 4, MD is 116, then E is Q divided by 1 plus M by MT. So if I put these values, Q was 8.2 divided by 1 plus 4 divided by 116. So if I calculate that one, then it will come as 8.2 divided by 1 plus 0.0344. So 8.2 divided by 1.0344, that will be 8.2 divided by answer. So 7.926. See the answer. 7.926 was there, so it is 93 like that. Because maybe after 2 decimal places, so 2 decimal places means 93 MeV. So for this question, we just need to know the expression for the kinetic energy and the Q value, kinetic energy of the alpha particle and the Q value of the system. So the relation is like that, the Q value is equals to kinetic energy into 1 plus mass of the alpha particle divided by mass of the daughter particle. So if I got to know the mass of the alpha particle, mass of the daughter particle, then we will, and also the mass of Q value of the system, then we can got to know the value of the kinetic energy of the alpha particle. Okay, fine. Now we can go to the next question. The element with atomic mass 120 alpha decays. Acha, it's very simple to the first one. So just quickly write here. Q is given as 10.4. Q is also given as E into 1 plus small m by md. Okay, maybe I should read the question at first. An element with atomic mass 120 alpha decays with Q value 10.4 MeV. The kinetic energy of the alpha particle is how much in MeV? Give up to 2 decimal place. Okay. So X 120, that will go as Y 116 plus alpha 24. Then Q is like E into 1 plus 4 divided by 116. E will be like 10.4, 1 plus 4, 116. 10.4 was there. So the kinetic energy will be 4 divided by 116, 1 plus answer, 10.4 divided by answer. Something like that, 10.05, 33 or something. So that is an MeV. I think it is 0.03 or 0.0344. Okay, 0344. So 10.053 MeV. So this is the kinetic energy for alpha particle for this question. Question number 11. That's it. Same question. Okay. That should be question number 12. Okay. So question number 12. Radon 86203 undergoes alpha decays to polonium 84199. The speed and parity of both the parent and daughter nuclei is found to be 3/2 minus. Which of the following are possible values for the relative orbital angular momentum of the alpha particle? That is nothing but a quantum mechanical question. Am I audible? Yes. So, in that question, radon 86203, that is going to alpha, and polonium 84199. So this is the process and the spin and parity of both the parent and daughter nuclei. Okay, let me write here. Radon going to PO 86, 84 plus alpha 2, 4. So IP is 3 by 2 minus 3 by 2 minus. Which of the following are possible values of the relative orbital angular momentum of the alpha particle? So first of all, they are asking that what will be the, okay, so there should be some IP of alpha, right? So I have written here explicitly IP radium is 3 by 2 minus, IP polonium is 3 by 2 minus. But I of radium, just focus on the I first. That should be equals to I of polonium plus I of alpha, right? So I of alpha, I means what? I is the total spin. Total spin is nothing but the sum of L plus S. The spin for the alpha particle is 0. So whatever the I is there, that is nothing but L, orbital angular momentum. So orbital angular momentum for alpha is exactly similar to the total angular momentum for alpha. Okay, this is fine. Now, as I have written here, I of RA equals to I of polonium plus I of alpha. This plus is nothing but not a simple plus. This is a quantum algebraically addition number. So that will be like I can have values from 3 by 2 minus 3 by 2 equals to 0 to 3 by 2 plus 3 by 2 equals to 3. Why I can do that one? Let's say, I mean this is the quantum mechanical addition. So obviously you can understand that what will be the value of L. I mean how many possible values of L should be there. Okay, so 0, 1, 2, 3. These 4 terms should be can be there for alpha particle because it's not a simple mathematical addition or subtraction, it's a quantum mechanical addition or subtraction. So that will give the value from 0 to 3. 0, 1, 2, 3. Any values of L are possible for alpha particle. Now, this is coming, this conclusion as L can be 0, 1, 2, 3. This conclusion is coming from only the value of I. But now we will calculate the value of parity also. Parity is like I minus was there for radium, IP was 3 by 2 minus. IP for polonium was 3 by 2 minus. As I already calculated for the I case, we got to know that the orbital angular momentum for alpha can have 0, 1, 2, 3 values. It can have these values from the concept of I only. Now coming to parity concept. Parity should be conserved here. So parity should be conserved means what? Parity in the left hand side, it was negative. That should be equals to right hand side multiplication of parities. So the right hand side multiplication of parity means for polonium the parity was negative. For alpha particle the parity we don't know. Let's say X. So X should be positive. Otherwise negative, this negative and positive will multiply and it will give us negative. But let's say if it is a negative value, then negative will give us positive value. So the value of the parity of alpha should be positive. Okay. Now if parity of the alpha is positive, then from the parity conservation law, tells us that parity of alpha should be positive. What does this mean? This means that minus 1 to the power L should be positive. Now see, previously we had L as 0, 1, 2, 3. L can have these 4 values. But if I put minus 1 to the power 1, then it will give us the negative value. But from the parity conservation law, we got that P of alpha should be positive. So, L can have the value 0 because minus 1 to the power 0 is positive. Minus 1 to the power 2 is also positive, but minus 1 to the power 3 is giving us negative. So, L can have the value 0 and 2. Now see the options here. Which of the following are possible values of the relative angular orbital momentum of the alpha particle? Orbital angular momentum of the alpha particle can have 0 and 2. So A and C are the correct one. I have written here that one, given this one and this one. But ato equals to ato, I is the orbital angular momentum of the alpha particle, the spin of alpha is 0. So I can have values from 0 to 3, 0, 1, 2, 3. Now the parity is not changed when radium undergoes decay to polonium. Therefore, odd values of L are not allowed, as radium and polonium both have odd parity. Allowed values of relative orbital momentum of alpha particle is 0 and 2. Correct answer A and C. Okay? Is it fine? Am I audible? Yes. Do you understand the point? Like why I have told that only the relative angular momentum for this alpha particle will be 0 and 2? I hope so. Okay, fine. We will check in the next question as well. In the next question, you can see that similar question is there. IR 77-167 undergoes alpha decay to RE 75-163. The spin and parity of both the parent and daughter nuclei is found to be half plus. Which of the following are possible values of the relative orbital angular momentum of the alpha particle? So the similar thing is there. IR 77 is going to RE 75 plus alpha. IP value is like half plus. We don't know about this one. So coming to the I right now, I can have from the I conservation law. So what will be the value of I for alpha? It will be half minus half to half plus half. So 0 and 1. So 0 and 1 can be the value. But you can, okay, so L can have, L of alpha can be 0 and as well as 1. Now, as from the parity conservation, in the left hand side it is positive, in the right hand side it is also positive, in the again the multiplication that should be positive, otherwise the right hand side will be not be the positive one. So if parity of alpha particle is positive, that means minus 1 to the power L should be positive, and L has the value 0 and 1, so L should be the value as 0. L should not be the value of 1 because minus 1 to the power 1 will give a negative 1. So L should have the value of A only. So which of the following are the possible values, but for this case values will not be there, only value will be there and the correct answer will be 0. I think it's fine. Can anyone confirm it's fine? Okay, very good. Now coming to the question number, I think I have done a mistake on the question numbers, maybe. that should be 12, that is okay, now it is fine, 12, now it is 13, now it is 14. Okay, fine. So question number 14, radon 222. Okay, radon 222, it was already given that radon 86 was there and 2222 is there. Radon 222 is a radioactive element with mean life of 5.5 days. Consider a hypothetical case of having one as isolated radon 222 atom. Which of the following statements is correct? Okay, this that is interesting one. Let's say I have an radon 86222 radioactive element which has a mean life, let's say mean life is like 5.5 days. I'll tell about what is mean life, but yeah, after that just see the question before that. Consider the hypothetical case of having one isolated radon 222 atom. Only one is there, that means N0 is 1. Which of the following statements is correct? It will stay without disintegrating for 5.5 days and then disintegrate. It is possible that it stays without disintegrating for many days after the 5.5 days. It will definitely disintegrate anytime within 5.5 days. Since it is one isolated atom, it will stay stable forever. So all the options are nothing but based on the meaning of mean life. If you see these options carefully, then you can see that all the options is nothing but in the focus of the mean life. What does it mean by mean value? So I have written here mean value. What does this mean? Half-life is the interval of time required for 1/2 of a radioactive sample to decay. Yes, that is simple. Therefore, okay, mean life is very similar to half-life. That is the interval of time required for 1/2 of a radioactive sample to decay. Therefore, after 5.5 days, which is the mean life here, they are talking, half of the sample will decay. So mean life you can say as a very similar of half-life, but for one, at least one, in that case they are telling that only one parent nucleus is there. So what will happen after 5.5 days and what will happen within the 5.5 days for this one radioactive element? So after 5.5 days, half of the sample will decay. But it is probabilistic. For a particular atom, there will be a probability of decaying or staying without disintegrating. I mean, just see these things. One particle radon 222, it is only one in number right now in the system. Only one particle. Only one radioactive sample is there. Now, half-life told us half-life is 5.5 days. So, for this case, what will happen? 5.5 days means after 5.5 days, we can have half of the sample at t equals to 0, whatever it was there, at t equals to 5.5 days, it will be half of the N0. This is the definition for half-life and mean life as well as. So, let's say previously it was 10 particles. After 5.5 days, it will be 5. Okay? But the thing is, obviously the quantum mechanical procedure, which is radioactive element to decay, that will be a probabilistic one. So probabilistic one means like either it will decay or it will not decay. For a particular atom, there will be probability of decaying or staying without disintegrating. There will be a probability. It is not like that ki exactly 5 particle will decay and 5 particle will be there after 5.5 days. It's a probabilistic thing. Okay. So for only one particle, I was talking about 10 particle, but let's say one particle. So obviously one particle means if it is a 5.5 days half-life, it does not mean that 5.5 is going to decay at 5.5 days and after 5.5 days 0.5 will decay. It should not be like that, because 0.5 is no, I mean, it does not have any physical sense. Yes. So for a particular atom, there will be a probability of decaying or staying without disintegrating. Therefore, it is possible that it stays without disintegrating for many days, even after 5.5 days also. As it is only one particle, it can decay within 5 days, 5.5 days, but it will not decay within 5.5 days, because the lifetime is 5.5 days. So it will not decay within 5.5 days. It can decay, let's say, in 10 days or 20 days or 25 days, something like that. But it can't decay within 5.5 days, that is for sure, because if it will decay only 0.5%. I mean, like, only 0.5 portion will decay. But 0.5 portion will decay, that does not makes any sense.
Excuse me, ma'am.
Yes.
Ma'am, and the question is it given mean life or half life?
Yeah, mean life, yeah, that is the thing. Mean life is nothing but the half-life for this case we are talking about. Mean life is, you can say, as the time at which half of the life, I mean half of the radioactive sample will decay. So like we are just going to understand what does this means about the half-life and mean life for this radioactive element case. Like, will it exactly decay after 5.5 days, or will it exactly stay remaining whatever it is there after 5.5 days or more? So for this case, if I just see the options, it will stay without disintegrating for 5.5 days and then disintegrate. This option can be a correct one, because as I told you that 5.5 days means like 0.5%. I mean 0.5 portion will be decay within 5.5 days. It does not make any sense. So obviously
Ma'am,
it
but
will,
if we were to consider the mean life of the radon nucleus, then it is possible for the nucleus to disintegrate within 5.5 days, right? Because mean life is, again, it's a probabilistic value, so it can, there is a probability that it will decay before the 5.5 days get over.
like, okay, so what does this mean you by mean life?
Ma'am, like mean life could be considered the average lifespan of a nucleus sample before all of them decay into the subsequent daughter nuclei.
uh, okay, just a minute. Like, if it is a half-life, let's say it is a half-life, then whatever I am talking about, this is the case. Like, okay, half-life is like 5.5 days, then 0.5%, I mean like 0.5% will be decay within the 5.5 days, and after 5.5 days it will decay rest of the things. So as the number of particle is only 1, so obviously it will not decay within 5.5 days, okay, and it will decay after 5.5 days if we are talking about half-life. But for the midlife case, as you were talking that midlife is the average value of this life, which will, I mean like, up to which, like, let's say 5.5 days. So that means this is the average lifetime for this radioactive element to decay into the daughter particle. So for that case, it can be possible that within 5.5 days it can decay. But if we are talking about half-life only, then the first option will be the correct one. Okay, I mean,
Ma'am, but half-life won't make sense, right? If we say half-life of an isolated radon atom, then that entire statement is
no,
logically not true, right?
statement is like that one, na? Like only one particle is there. If half-life is there, let's say 5.5 days, that's why I'm talking, na? Like 0.5% is going to decay within 5.5 days, and after 5.5 days the 0.5% is going to decay. But that does not make any sense, because 0.5 means what? Half of the particle. But half of the particle should not decay in any way. So that's why, like, whatever, if it is a half-life thing, then it will say, I mean, it means that after 5.5 days it will decay. If the half-life is there, I mean, like, let's say in 10 days or 15 days, it will decay. It will decay as a whole. Otherwise, half-life is nothing but 0.5%. I mean, like, half of the parent nuclei. So obviously for one particle it does not make any sense. That's what I wanted to tell. So, but if midlife is there, then as you told that the midlife is nothing but the average of all the lifetime of that lifespan of their parent particle to, I mean, within that 5.5 days, it will decay to the daughter particle, then it is possible that it will disintegrate within 5.5 days, or it can be also possible that it will decay after 5.5 days also, like it is a probabilistic one. It is possible that it stays without disintegrating for many days after the 5.5 days, that is also possible. But for half-life, if I am talking about half-life is good for A as well as B. It will definitely disintegrate at any time within 5.5 days. That is also not correct for mean life also. Like, it's totally a probabilistic thing. That's what we are right now focusing here. Mean life and half-life, whatever is there, that will be totally a probabilistic case. And for probabilistic case, we don't know at which time it will disintegrate and which portion it will disintegrate. So for the mean life case also, it is possible that it stays without disintegrating for many days after the 5.5 days. That is also fine. It will stay without disintegration for 5.5 days and then disintegrate. That is also fine. It will definitely disintegrate, that we can't say. So the question number C will not be going to happen because it's a probabilistic one. And since it is one isolated atom, it will stay stable forever. That is also not correct, because we are talking about mean life and half-life for this isolated particle. So it is not, option number D is also not correct, that if it is an isolated atom, it will stay forever.
Ma'am, instead of it will stay stable, if it was it might stay stable, then that option could also be correct for mean life.
It might stay stable forever will not be the correct one. Like, forever means what? So obviously it will decay, but when it will decay, that we can't say confirmly. But
exactly, ma'am. So
yeah.
it could go on forever, right? We
No,
can change
not
the definition
forever.
of something.
Forever should not be there. It will decay, but at which time it will decay, that we can't say. So forever means what? It will not decay anymore. Do you understand the language actually? Like, forever means what? Forever means it will not decay anymore in any time. That will not be the correct one. And whatever it is in C, that it will definitely disintegrate, that is also not correct. It can decay within 5.5 days, it can decay after 5.5 days, but it will decay. That is the confirmation. But when it will decay, that we don't know. It's a probabilistic thing.
But if the decay of an atom is probabilistic, then we can say that there is a chance that it will never decay at all, right? Because any time frame we give it for it to decay, there is a time frame where it will never decay at all, because it's probabilistic after all.
Probabilistic is fine, but probabilistic up to which time, that we can say. Like, let's say mean life is 5.5 days or half-life is 10 days or something. So it is probabilistic that it will decay, half of the, let's say we will talk about half-life as 10 days and 1000 particles are there. So it is probabilistic that 500 particle will go within 10 days and rest of the 500 will be remaining after 10 days. That is most probabilistic thing. But it can also possible that 500, but it can be possible that only one is decay within 10 days and rest of the 999 particles are decaying in after 10 days. But it will not be the case that any 1000 particle is not going to decay. That will not be the case anymore.
Yes, ma'am, but that's for a sample. We are only talking about an isolated radon atom.
So radon atom, it's okay. I was talking about 1000 because of the integer numbers and all. Let's right now talk about one only. So for this case also the same thing will be there. Let's say it is a 10 days half-life. So one particle is there and it will, whatever it is, say that it will stay stable forever. That will not be the correct one, because it will decay, but obviously there is some probability to decay within 5.5 days, or there is some probability it will decay after 5.5 days. But it will decay because it's a radioactive element. Radioactive element means it should be decay, but at which time it will decay, that we can't say certainly, because this is a probabilistic thing, like probabilistic approach. So Whether it will decay or not, that we can say, but when it will decay or not, that we can't say. So whatever the D option is there, it will stay. It will stay means obviously they are saying that it will definitely stay stable forever. That will not be the correct one. It will definitely disintegrate at any time within 5.5 days. That is also not correct. It can disintegrate within 5.5 days or after 5.5 days. That is fine. Okay, so okay, fine. I think there is no other question for today's class, but let me go through from the very first. If you have any doubt, you can just ask me. This is the first question about the single vertical cell model. This is the second question, activity of a sample of radioactive element. What is this? Okay. They are asking for the capital N. Yes. Then this is the same question with the different numbers. They are asking for the capital N. Then this question they are asking for the capital N as well, but with the help of NGO to the minus lambda T expression. Then this is the question, okay, similar question, that n equals to n0 to the minus lambda T. Then there is another question, okay, this is the 36% and for 64%, how much it will decay. Then this is the half-life given is there, and what will be the daughter particle after 1 alpha decay. Then okay, particle are there for the Q value. What will be the value of Q value for this question? And this is also similar. Then this is the atomic number. Kinetic energy expression is there. This is also kinetic energy calculation. This is the spin and parity calculation. So quantum mechanically, what will be the value of spin parity? This is also the similar question. This is the radon midlife and half-life what we were talking. So these are the 15 or 14 questions, 14 questions. So do you have any question for all these 14 questions? Any doubt? See, whatever the midlife and half-life we were talking, that the main motto of this question was that the quantum mechanical process is probabilistic, totally probabilistic. So that is the main motto, to show that. So probabilistic means it can happen within the lifetime, within the day, whatever we are mentioning, but it can't happen within that within that time, whatever we are mentioning. But it is not that it will not happen anymore. Okay. The main motto or main outcome or take home message, you can say, for this question is like that quantum mechanical question, radioactivity is nothing but a quantum mechanical phenomenon. So it's totally a probabilistic phenomenon. Okay. So is there any other question?
No, ma'am, not from my side.
I can see, I have already checked your this year assignment for week 3. I think most of the questions are very similar, whatever I was explaining this year, this class. So that will be little bit very similar to your this year assignment week number 3. But maybe there will be some more extra questions, obviously. So if any questions are little bit problematic for you for the week number 3, then when the date, the time will be over, after that we will discuss about the week number 3. Obviously not right now, because I think the date is still there for submitting the week number 3 assignment. So after over this date, then we can discuss about these questions. If you have on these questions anymore, then we will discuss that one in the next class, or maybe if the time will not over in the next class also, then we can discuss in the next class. or any type of questions for the like first week 0, week 1, week 2, whatever is there. If you have any doubt, then you can ask me after obviously completing the date, so that we can answer, we can discuss that one in live session, not within the date. Okay. And I think whatever the questions are there, it's totally, I mean, very similar to whatever we are discussing right now. So it will be very much helpful to have a idea of the assignments of week 0, 1, 2, 3 and all the rest of the weeks also. So as I told you that this mass and atomic mass and nuclear mass, that will come I think week number 4 or week number 5. Then also we will discuss about these things in more detail. What is atomic mass and nuclear mass and how we will calculate this conversion and all. So just be tuning and we will do that here. Okay, so maybe there is no other question. Then we can go to stop today's session and we will come in the next class. Is it fine?
Yes, ma'am.
Okay. Okay, so bye bye. Good night.
Thank you, ma'am. Bye, ma'am.
Thank you, ma'am.
Bye.